In our previous video, we created a linear regression model and we looked at the assumptions of linear regression. So now let's look at the idea of overfitting and adjusting your model based on the number of variables that you have. So we create a linear regression model and we are trying to find one that has a higher R squared. So we are picking more variables. So we are doing a multivariable regression model, more variables, more independent or predictor variables used to predict whatever we're trying to predict. So we're continuing our discussion about linear regression. So what we're trying to predict is a measurement, so interval or ratio data that can have fractions. And so as we build this model, we tend to kind of look for a model that fits our data really, really well. Well, this is overfitting. The challenge with overfitting is that as we adjust our linear model for every little change in the data, we add more and more variables to help us do that. The problem is that it fits really, really well for our data set that we're using to build the model. But then when you add new data that wasn't used to build the model, it fits terribly. And so we have this idea of overfitting. So I'll just show you here. This is from one of our previous videos, and this is the complaints data set from our forecasting chapter. And in that particular one, we built this model. So here's the complaints, and we built a model, a polynomial of degree 4. So you can notice that as we add more levels or orders to our polynomial, we can get every single curve in that. But the problem with a polynomial is that no matter how many orders you pick, in the future, it only goes up or down. It doesn't keep its wave. If you want waves, you're looking at seasonality, you're looking at medium-term forecasting, you're looking at SARIMA or profit models. But if you just use a polynomial, it can account for every little change in the current data, but for the future, it only goes up or down. So this is an example of overfitting. We're taking into consideration every little movement in the data in the past, but the problem is the future is going to be horribly inaccurate. So we want to kind of have a compromise between an underfit model that doesn't take that into consideration and an overfit model, which is terrible. So underfit, terrible accuracy for the current data set used to build it. Overfit model, huge accuracy for the data used to build it, but all future data, terrible accuracy. So we're looking for a compromise in between. So what we can do is if we have a linear regression model, we can do what is called ridge or lasso regression to help adjust for the overfitting. So we can still have lots of variables, but we reduce the impact of the variables. So ridge regression adjusts for the overfitting by making the coefficients smaller. We minimize the impact of each of those predictor variables. Lasso regression adjusts for the overfitting by turning more of the coefficients 0, so basically ignoring some of the variables. This simplifies the model, right, because you're using less predictor variables. It's popular if you have data, so you're trying to predict something, but you have a lot of zeros in your data. So think about it this way. I'm trying to predict dollar value of sales for our company. And we are looking at the sales of one item. Well, it only goes to a couple people. So most of that variable, the data for most of our customers is 0. And then we have another item. Well, it only sells to a small group, different group. So it's mostly zeros for everybody else. So that's a sparse data set, right? It's mostly zeros. And then for some people, there is going to be data. We looked at our classification models for images, those letters or numbers. Most of the page was white and only certain pixels had any grayscale to them. And so that's a sparse data set. If we were trying to create a linear regression model, we're trying to predict some interval ratio data, but many of the variables don't have, it's not they're missing, it's that they don't have a value. And then others have values, then we would use the lasso regression because it just removes some of the variables. The ridge regression method reduces the impact. You still keep all the variables, but we're making the impact they each have a bit smaller to reduce the overfitting of the model. So we're going to look at ridge and lasso regression. Okay. As we assess our regression models, there are different ways to assess regression models. And they are the same like what we do with a forecasting. We talked about mean square error and we talked about forecasting models, and it takes the difference between your actual value and your predicted value. So actual minus predicted squared, and then it takes the average. So it's going to emphasize when a single data point is really far off. Okay. There is also what is called root mean square error. Root mean square error is where you take the square root of the mean squared error. It determines the variability in the measurement error. When we look at just the average error itself, not the squared, but the average error, it should be 0. And then the root mean squared error shows us how much variation there is from that 0. Okay. Now, as we look at assessing our regression model, we've talked before about R squared, how much variability in your X explains the variability in your Y. So we'll look at R squared as an assessment. As we start to get into neural networks, which will build on this work that we're doing here, then we start to get into how we're further assessing our model with our loss function, and then mean squared error is going to be part of that. Sometimes you see the term cost function, the cost of the model. So same kind of thing. It's all about the size of the error, the size of the measurement error, the size of the residual. So residuals, measurement error, loss function, cost function, these are all kind of interchangeable. How far away are we looking at from what we actually have and what we predicted? Now, we talked before about the fact that when we build a model, we can get things like R squared, and we can measure our measurement error. We can measure our residuals of the current model. If we want to know if we had different samples, if that's going to give us different results, then in the machine learning world, we would do things like k-fold cross-validation, which is pull a different sample from the data set and then look at how well it fits to see how much change there is. So we can use that k-fold cross-validation that we talked about previously as well. So we're going to dig into those as we look at our ridge and lasso regression. All right, if you're working along with us, we are, just go back here. We are at drstephpowers.github.io/BIA. We are here in chapter 10 looking at regression, and you are opening this in Google Colab. You are logging into your Google Drive. You are saving a copy of this to your Google Drive, and we are actually going to be using a data set that's in here somewhere. We're going to use this wine data set, which you can't see because it's at the bottom of the page. All right, come back. All right, this wine data set that's right here. So go in and you're going to download that wine data set. So if you click on it, you can download it, dump it into your Google Drive, and we want to link that to our drive. So where am I? I'm here. Okay. And we are going to, before we can do our ridge or our lasso regression, we're first going to have to import our data in. So you're going to dump that into your Google Drive. You are going to then use this line of code here to link your workbook and your Google Drive together so it can pull your data set. You're only giving it permission for your Google Drive to access your Google workbook, not everybody else. So just select your Google Drive and hit accept. Here we're importing the wine data set. I have mine in the Google Drive in a folder called BIBA Handbook inside a folder called Chapter 10. And it's called Wine Quality White is what we're using. So it's separated by semicolons. So that's what that notation that my face is covering right here, separation here. So we're going to import that in. So locate where that is in your drive by changing out this piece right here. And then let's import this data in. All right, so what we're going to do is we're going to try to predict quality. Now, we are using this data set incorrectly. That's because if you look at this quality measurement that's right here, you will notice that this is essentially ordinal. Scaled is probably from 1 to 10, the measurement of quality. So if we are doing linear regression, we are assuming that the variable we are predicting is continuous, so it can be fractions, it's not a count, or ordinal. To truly analyze this data, what you would actually do is you would take that quality data variable and separate ones that are listed as quality and ones that are listed as not. So maybe 1 to 4 is not quality and 5 and higher are good enough. Make it binary, make it logistic regression, see if you could build a model for that. So that would be a more appropriate use of this data set if you're trying to predict quality, because this quality here is actually more of a Likert ordinal data, not a count, not a measurement. And so when we have ordinal data with regression, we turn it into logistic, make it 2 categories, good and bad. Okay, we're going to pretend that this quality measure here is continuous, some kind of measurement of quality that can have continuous or have fractions of values. All right, so what we're going to do though is we're going to simplify this naming scheme here to be smaller. So I'm going to replace some of the names just to make life simpler because some of them are kind of complicated and repeat. So I'm just going to rename things like fixed acidity to acid, volatile acidity to vola acid, so we have them separate. So that's what this line of code here is, just to kind of simplify things a bit. Okay, so now pause the video and create a logistic regression model using some of these variables. If you're using SMF, you leave it as this one table that includes the quality that you're predicting. If you are using sklearn, then we'll identify which variables for each. So to do this, right, so let's do the SMF model. We're going to need, as we go back to reference the code from earlier, is that we're going to need to make sure we import stats model formula API. I'm just going to scroll down and paste it in here. And we are going to need, we already have our data. So if we go back and look at the previous example, here we were combining it. In this case, if we're not going to separate testing and training data, so we're not going to do the split first, then we don't need to split and then concatenate back. Instead, we'll just use the full data set we already have. We already did the renaming, so now we have a table that looks like this for our wine data set. So we're just going to need to copy the code here where we call the model and fit the model. So I'm just going to pull this down. So we import SMF. We're going to do ordinary least squares using SMF. We're going to predict quality, make sure it matches. So quality is lowercase here. And then we're going to pick a couple of variables that we're going to use. So I'm just randomly picking some. Chloride, sugar, I don't know, citric. Just randomly pick some things. Density. And then the name of our table is not reg. The name of our table is wine. So we're going to call the model, fit the model. We named it OLS reg. And then we need summary. So we do that, and what we find here is that chlorides is statistically significant. Remember, see, they're both negative. Sugars is statistically significant. Citric is statistically significant, as is density. So combine those 4 variables, have an adjusted R-squared of 18.8%. So we're really not explaining tons of the variation in quality measurement. Less than 20%, even though we have 4 variables there that are statistically significant. We can see though that when chlorides go down, quality goes up, so they move in an opposite direction. When density goes down, quality goes up, they move in an opposite direction, whereas more sugar, more citric seem to increase quality. So we don't have a very high R-squared. So we would think, okay, let's add more variables to see if we can better create a model to predict quality. Now, as we start adding tons and tons more variables, we have that risk we talked about of that overfitting. So let's look at ridge and lasso regression in terms of how that deals with that overfitting. So what I have here is that I have pulled or dropped out the variable called quality from this table. And that's because when we do our ridge and lasso regression, we are going to have it kind of separate out we have the variables that we're using to predict, and we have the quality that we're trying to predict. Rather than write in for this test train split section every single variable in this long list, because I want to use like all of them, I am instead going to create two tables. This table here called wine2 is everything except for the quality variable. So this will be all my X's. So I'm going to call this wine2. I'm going to drop the column that's called quality. And when I look at wine2, you can see that it is that same table. It just doesn't have the quality variable. And that way, when I go and do my test train split, I can say for the X variables, just use this wine2 table. It'll cover all of them. And then from the other table, I can pull that quality variable to be what I'm predicting. Okay, so we did that. We're now going to do some ridge regression. When you do ridge regression, it's from sklearn linear model. We're going to import ridge regression. Ridge regression only works with linear. And then we're going to assess the model by looking at mean squared error and our R score. Okay, so let's make sure we import those in. We're going to separate our data into training and testing data. So we're going to use all of those variables are going to be the X, and then quality is going to be the Y, and we're going to have a test size of 20%. We don't need to include a stratify because this is a continuous variable. We could include the shuffle if you wanted to do that to make sure, just in case the data is in some kind of ordered sequence rather than random. If you're doing ridge regression, it's just like all the other ones. Call the model, fit the model. We can get coefficients and intercepts. We can predict the values. So when you do ridge regression, you have to set an alpha. Alpha is how much of the variance of the estimates are going to be reduced. Okay, so when we do our alpha, the bigger the alpha, the more we're going to limit the impact of the variables. Okay, we'll actually do a analysis here called ridge CV. It's going to help us pick the alpha. So we'll just start here with an alpha of 20, and then we'll do a comparison. All right, so alpha equals 20, call the model ridge, fit the model, and then we're going to get our coefficients here and an intercept. Now, because we're doing this ridge regression, which is adjusting the weight it puts on the variables, it is changing the coefficients. So in this particular case, when we're doing ridge regression or lasso regression, we are typically doing these as part of a neural network or machine learning process where the emphasis is on the prediction as opposed to the model building itself and the value of the coefficients, because we are intentionally manipulating the coefficients so that we can reduce the overfitting. Whereas in the previous models, when we were doing logistic regression, our focus was on to find those coefficients. So we could say this is the impact this variable has on what we're trying to predict. Here we're going back to that more machine learning method where we are focused on the prediction as opposed to the impact of a particular variable. Okay, so we measure it based on how well it predicts the model. So we called the model, we fit the model. We now need to predict with the model. So we're going to predict with our test data and get those values. And then what we're going to do is calculate the mean square error. So we'll use mean squared error and we'll compare the actual data, the tested data, and the predicted data. And we have a mean square error of 0.65. When you're doing ridge regression, there is an amended version of R squared called the ridge score that helps you to see and compare your models. We can look at with different alphas what's the better fitting model. So you can think about the ridge score as kind of R squared. So when we run this here, we can see that we have an R squared of 23.8%. Okay, so recall just a moment ago when we built this model here, we were looking at a model with our 4 variables that was sitting at that adjusted R squared at about 18.8%. So we're trying to get a higher R squared, higher, more of the variability, in this case, the quality, being predicted by the variables that we have. All right, so we're not sure that the alpha we chose is the appropriate alpha. So there is something called Ridge CV, which uses that cross-validation that we talked about previously. So remember K-fold cross-validation scores when we were assessing our classification models? We can use that here as well. And so the Ridge CV uses that cross-validation. So you need to import it, and we can give it a range of alphas. So here, this is an alpha of 1 to 100 in increments of 5. So it starts with 1 and then 6 and then 11 and 16. So you can see here, you can of course change that to be a different range or different increments. It iterates through and runs it many times. So of course, the more alphas that you have, the longer it's going to take for this to run. All right, so what we're going to do is we're going to do a ridge CV, and we're going to have alpha equal to this list that we have here of numbers. So it'll try out all the different ones. Okay, and the idea is it's trying out and trying to find the best alpha, and then it will fit that model. And we can then look at the coefficients, the intercept, and how accurate that model is. So let's go through here. So it's going to do it with all of our different alphas. Okay. And we can call the coefficients, we can call the intercept. Notice here these coefficients from this model, they are very small. Notice what they were previously, not as small. So as it's running its cross-validation and going through all those different alphas, it's actually increasing the alpha more than the 20 we initially set it at and minimizing them further. Okay. So based on that minimization of the coefficients, we can then predict our values. We can get a mean square error. Our mean square error before was 0.65, and here we're about the same, mean square error 0.65, and you can see our ridge score is now at 27%, before was at 23%. So we're increasing the alpha, it's minimizing the coefficients for the variables further, and at the same time, it's getting us a model that better represents the variation in what we're trying to predict, which is the quality, using all these variables. So what we're doing is we still have all these variables and what would be an overfitted model, but we're kind of smoothing this out by minimizing the impact of those variables to get a model that is better prediction for the future. Okay, and that's why the R squared, or that ridge score, is going up. But at the same time still fitting the historical data as well. All right, where am I? Okay. You can look at that ridge score with both the testing data and the training data. What we want is we want not just a high score when it comes to the training data, because we built the model on, but we want it as a high ridge score with the testing data. Remember, the problem with the overfitted polynomial is it fit the old data really well, but then in the future it was really far off. So what we're doing is we're taking lots of variables to help increase that R squared, but then minimizing the coefficients so that it not only explains the historical data, here we're at 27% for the data used to build the model, but is also equally as good in terms of that explaining that data that wasn't in the original model. So that's this here. So we want these to be close to each other. I mean, it's always going to go down because this data wasn't in the model and this data was, but what you want is to not lose a ton. with the new data set. We could look at the error. So like with linear regression, we could check our assumptions. So we would find using NumPy the difference between our actual values and our predicted values. Technically, they should go the other way around. So we're doing y-test and y-predict. Okay. And then we can plot that information. It should look like random scatter. Remember our discussion that it should be random scatter. There should be no pattern to it because otherwise it's not normally distributed. It should be homoscedastic, which is that the variability, when we look at our graph here on the left side and on the right side, should be the same. So it should look like random scatter. And then to test that normality assumption, we'll use Skippy stats as stats. That'll give us the t-distribution. And then we need to make sure we have also imported, where is it? Go back. This stats model.api as SM. We're going to need that as well because when you look at this QQ plot, that QQ plot comes from statsmodel.api as SM. So we'll run that, we'll create this, and we're looking for it as it fall along the 45-degree line. So we're pretty close here. I mean, we can see that the two extremes, we're not quite there. They're kind of both on the lower end, so we're kind of tailing off. Not as many of the two extremes as is predicted by the, we don't have as many of the two extremes as we would have in the t-distribution. But we're pretty close to normally distributed. So here we've created a model. We can increase the R squared and how well it fits, increasing our ability to predict because our focus here is on prediction, not on explaining the model. And we can do that with ridge regression. So it allows for lots more variables in a linear regression by reducing the size of those coefficients. And so you can use this ridge CV to help you figure out what the appropriate alpha is to do for the model. In our next video, we'll look at lasso regression. The difference between ridge and lasso is that while ridge made the coefficients smaller, lasso is going to make more of the coefficients 0. They're both doing the same thing. They're trying to increase the R squared, increase your ability to predict whatever variable you're trying to predict, which in this case is quality, by using lots of variables, but adjusting for that overfitting that causes that the model to fit really well on the data you built it on, but not well at all on the data that you didn't. So in our next video, we'll do lasso. Both ridge and lasso regression are used as part of neural networks, and we'll get into neural networks in later videos.